This lecture is going to be a continuation of the previous lecture where we discussed the case study for the design of the gearbox. So let's go over the requirements for the gearbox case study, and then we'll walk through area by area, outlining what we're going to do. So if we look here, the gearbox case study, we have a manual, and the manual is a step-by-step, again, similar to the main project, where we lay out the design constraints and requirements, and then we have one section after the other going through the various steps. So if you look here, we have design project requirements. To define this introduction, we have a MATLAB program that is half finished, so you would have to finish your other half, and this is the best way to learn, is by mimicking what we have done already. And we have a script, and the script is also provided with some areas that you have to fill in. Then we just go step by step. The first step is to define the torques and how basically we want to transfer a level of power, and the transfer power is at a certain efficiency, and we have an input speed and output speed, so there's a gear ratio, and to achieve that, the torque is going to have to be going up and down between different parts of that gearbox. And that will be described in this section. Then the gears that we have to specify, maybe 5 gears, 6 gears, 7 gears, 8 gears, depends on the gear ratio between input and output speed. That is called the gear train. So we would have a section to specify the number of teeth and the pitch and the size and the diameter and the material so that we can go ahead and purchase these gears in order for us to put together the gearbox. And then we would do gear analysis. That's a gear train going from input to output, as I mentioned before. These gears are going to be assembled on various shafts. There might be 3 shafts or 4 shafts, depends again on how the margin between the input and output speed. And each shaft has to have a set of requirements, sizes, length, and structure. The shaft has a certain structure where we will be able to attach the gears. So that's the kind of the layout that we have. And the shafts will have forces and torques and moments. So these are 3 different types of loading, and those will induce deflections and induce stresses. And the stresses will be 2 parts, one steady state and the other part is going to be fluctuating, and the fluctuating stress will induce fatigue. So for complete shaft analysis would entail deflection, stress distributions, stress concentrations, failure analysis, fatigue analysis. Finally, once we have all of the shafts done and all of the, let's say, 4 shafts done, 6, 7 gears done, then we'll have to assemble the gears on the shafts, and to assemble those, we require to have grooves on the shafts, we have shoulders, we have keys and retaining rings, and ball and bearings. So all of that will be in the last part of the report. So let's get step by step. In this step, we design the high-level project constraints, and the constraints would be the input speed and the output speed. Here, the gearbox is very simple, and it's a velocity reducer. So we want to reduce the input RPM from 2,500 and get the output RPM to 50 RPM. And in order for us to do that, we would like to transfer 5 horsepower. So the reduction in the speed would mean that you would have to come in, because the input speed is very high, so you would have to come in with a small size gear with a smaller number of teeth that rotates very, very, very quickly. And then as you go to step down the speed, then you have to transfer to larger and larger gears, and to achieve that kind of gear train ratio that we are talking about. So the gear train ratio is defined as the number of teeth or the number of revolutions for the output divided by the number of revolutions for the input divided by the number of revolutions for the output. So in this case, we have, I have to read it correctly here. The input is 50 RPM, and the output number of revolutions is 25 RPM. And lowercase n here is basically the total number of teeth for the input divided by the final number of teeth. In other words, n input omega input is equal to n output omega output, and omega is the RPM. So the number of teeth on the gears will be inversely proportional to the speed. So having said that, the total ratio that we would like to use to reduce the speed is 50 times. So we want to reduce the speed by a factor of 50. That is usually very large, and from practice, we usually limit the reduction to about 10 or less than 10, which means that it would be advisable if we would make the reduction over 3 stages. And here you have stage 1, here, stage 2, and stage 3, such that you have the reduction, overall reduction of 50. So that would be a gear train, making a gear train. We'll go into a lot more detail in the course towards the end to define these gear train ratio. Once we have defined the gear train ratio, then and the gears, so we've found that in this case we have to have 1, 2, 3, 4, 5, 6 gears and maybe a couple of shafts. So you have like an input shaft here and an output shaft, and here's a bearing, and then this is the gear, and this is another gear, maiden gear, and so on. So you have all of the gears. That's kind of, you would make the shaft layout. This is just for 2 parallel shafts, but your design could have several shafts, and some of them could be at 90 degrees, making it interesting to kind of lay it out in the minimum volume possible for the gearbox. Here is an example for a project where we have the input shaft is right here. So the input RPM is 2500 RPM here, and this has to go very, very fast. So let's give it 2 arrows, and this is coming in, and the requirement is to transfer the power at the output shaft will be at 90 degrees. So the output shaft, let's say, is here, and the rotation is 50 RPM. And to do that, we have 1 contact between 2 gears here, another contact between the 2 gears here, and a 3rd contact here between the gears. So that defines the kind of shaft layout. And you can see here I have bearings, these green ones here, the bearings that need to be also analyzed in the design. So that's the part that will be like a strategic part for your project, where you lay out the shafts in such a way that you would have the most compact system possible. In other words, we try to eliminate this space, eliminate any spaces to make everything as close as possible so that we can achieve minimum volume. Here is a final component list. So you produce a component list We have we will study several kinds of gears. The first and simple one is a spur gear, and then we would have helical gears and maybe bevel gears. These are 3 different types that might be used. Some of you might even use worm gears for other applications. So the components are listed here. We have bearings, we have rings, retaining rings. You specify the material and the manufacturer and the part number. So this is pretty professional to that level, where you can, once you design the gearbox, you can go ahead and actually purchase the components and manufacture others, maybe machine them, and then you would have to put it together if you were to make, say, a small factory, or you are actually participating as a designer in a large factory. Then your responsibility would be to have purchase components and manufacture components. Things like intermediate shafts, output shaft, you need to specify the raw material. This is IC 1030 steel, and then the vendor, McMaster car, the keys, you specify the keys and the bearing sleeves. All of this is part of the design, so it can be, at the end of the day, when you have your final report, you'll have a complete design with all of this list. The shaft properties that we have, if we select different shafts, and they come from material stock with a price tag, and the price tag is related to their properties. The cleaner the material is and the longer it can survive, the higher the cost. So this is identified as the elastic modulus, the yield strength, the ultimate strength, and then the number of cycles to failure. That's the fatigue part that we have to also design for. So the design requirement is part on us to reduce the loads and to make it live longer, and then part on the product itself, where we can use higher grade materials to have longer lifetime. Here's an example for the bearing reaction forces, and the bearing reaction forces that we have here are we can see that I have to define the bearing here and the bearing here, and this is a helical gear. So you can see the helical gear. The interesting part about the helical gear is that at the contact point right there with the other gear, it will have a radial component of the force, a tangential component of the force, and an axial component. So this axial component has to be taken by a retaining ring so that this doesn't slide out of the shaft, and the radial component is going to cause the bending of the gear teeth. So we have to design the gear teeth for that bending stress. Here's a free body diagram for shaft 2. Again, I have radial component, radial coming towards the center, so the centering component. Tangential is the one that actually drives the gear to rotation. Axial is not so good because it actually can make the whole system slide, and in order for us to prevent the sliding, we have to put these retaining rings at least on one side, depends on where the reaction force is, so that we can buck this force with the reaction. As a result of the free body diagram, we produce shear and moment diagrams for the input shaft, and these are 2 shear diagrams. You can see that the shear is constant, and because the forces are point forces, we will discover that with point forces, the shears are pretty much constants except for jumps where the force or the contact is. This is where we have a gear. So each shaft is going to have 2 planes, and we would have shear force diagram and bending moment diagrams on each of these planes. In addition, we would have to compute slopes and deflections. So you can see here, this is the slope and this is the deflection. And the deflection is a formula that we will develop, which means that if we find the moment distribution along the shaft, then we will find that if we divide this by the modulus E and the moment of inertia I, that gives us the curvature of the beam. Curvature is a second derivative. So once we find the moment diagram, we integrate it once, we find the curvature, and the curvature we integrate it once, we get the slope, and then twice we get the actual deflection. So the design also would have a limit on this maximum deflection. Like you can see, a maximum deflection is 2 times 10 to the minus 5 meters, very, very small, like 20 microns, and that is very small and rigid, like very nice system. But in other cases, if you have the shaft very long, then the deflection could be substantial and could violate certain design requirements. In addition to the shear and bending diagrams, we also have a torque diagram because there's going to be an input torque and output torque, and the torque diagram is also given here that has to be included into our analysis. So next step is going to be the gear train analysis, and in this system we have 1, 2, 3, 4, 5, 6 gears, and we specify the type of the gear. This is helical. The 1 and 2 are helical, and then 3, 4, 5, 6 are spirit gears. Here are the number of teeth. The input is large, from input small because it rotates at high speed. Output is large because it rotates at lower speed. Small, large, small, large, as you can see here. So in this case, I'm stepping I'm stepping down the speed a little bit every time, every stage. So this is 1 stage, 2 stages, 3 stages of stepping down in a gear train. And we define the pitch, the diameter of the gear, so it's a 1.5 inch, 6 inches. So these diameters, like 10 inches, is pretty big gear, and those can be also variable depending on the design. So you need like a computer program so that you can play with the parameters and reduce the size of the gears and make it as compact as possible. This is the face width, and there's limitations on the width of the face. If the face of the teeth is very wide, then you can carry higher force, higher torque. If it is short, then you can't carry that much torque and force. And I'll show you the examples here. Like in this example here, this is the face width is pretty wide and in good shape. And here, and this is also wide. You can see like the face width wide. Like from here to here, like this is the face width. This is, you can carry a lot of force. Of course, if you make it shorter, then like this level here, this is not much more force. But if you make it very wide, then you can carry a lot of force on this. Of course, you cannot make it very, very tall like that because it wouldn't be a gear, it would be like a cylinder. So we have to kind of, we have limitations on what we can do. So the shafts, after you design them, they are going to have some structure like this. You have a bearing with a diameter D1, and then you're going to step up from D1 to D3 with a intermediate diameter D2. So there's a little bit of a notch here. So you're going to increase the, you're going to have a bearing, and the bearing has to sit here. So the notch is to locate, it's a locator, so that we make sure that these two surfaces, interfacing surfaces, are in contact all the time. However, this area here is high stress concentration. We also have another step here to D4, and then you step down to D5, to D6, to D7. So we have 7 different diameters along the shaft from one end to the other. We have 2 gears on the shaft, and the gear has to be attached. And the attachment are 2 parts. One is by the shoulder, so we just kind of make sure that it is tightly attached to the shoulder or pressed against the shoulder with a retaining ring. And here we might be able to mill into the shaft itself and put like a key. So the key is going to be inserted in this milled region to make sure that the gear doesn't slip out. Now the milling is going to cause a stress concentration here, stress concentration here. So we will learn that this is going to be a critical part of the design that needs to be analyzed in detail. And once we finalize the shaft, so each shaft, so if you have like 3 or 4 or 5 shafts, each one is a final shaft design. We would have to produce a machine drawing that is ready for manufacturing, because that would be turned and in a lathe machine from the stock, like you have a rod that you bought, and that will be, you can turn it into a shaft, as you can see here. This is the final analysis, the final assembly, and I'm going to show you 2 designs. This design here, we have an input shaft and an output shaft, again at 90 degrees. But you can see that the gears, the face width here is very, very small, very skinny. You have a spar system, very wide open here. So it will be kind of large. And if you put it in a gearbox, then this will be your CAD design that you will have. A lot of open space that is not used. Another example, this is a final example. We have, this is a little bit more compact. And you have input shaft here and then the output shaft, and the gears have decent size faces that can take the forces or the torques and give us the required reduction in the speed. So with that, we will end the lecture, and we will see you in my next video, and thank you for watching.